Welcome to NPTEL online course on fractals and multifractals. In the last lecture series, we have defined what is the S-dimensional Hausdorff measures. Then we have discussed some properties of S-dimensional Hausdorff measures. In these lectures, we are going to discuss what is the Hausdorff dimensions. Based on the Hausdorff measure, we are going to define the Hausdorff dimensions in this lecture. I just recalling what we discussed in the last lecture, and we defined the S-dimensional Hausdorff measure. Suppose that F is a subset of R power n and S is a non-negative number. For any delta greater than 0, we define this Hs delta of F infimum of sum of mu I power s, such that this ui is a delta cover of F, where this infimum taken all the delta covers, that means ui covers all the covers. Here that modulus of ui denote the diameter of the set ui. This is a positive number. Then for all the delta cover, we need to find this diameter. Since if you are taking u1, it has the different sets which covers the F, we need to find the diameter. Then among all, we need to take the infimum. Thus, we look at all cover of F by sets of diameter at most delta, and seek to minimize the sum of the sth power of the diameter, so that this H depends on delta as well as S. Whenever this delta tends to 0, this limit exists, neither it is 0 or infinity or any positive number, this limit exists. If delta tends to 0, this Hs of delta of F is called the S-dimensional Hausdorff measure of F. For any F belongs to R power n, this limit exists. Then we discussed that Cantor set in which we obtained the S-dimensional Hausdorff measure of the Cantor set. Whenever we are finding the 0-dimensional measure on the Cantor set, we get the number as infinity. When we apply the one-dimensional measure, that one-dimensional Hausdorff measure on the Cantor set, we get the number 0. So, we guess that there is a number in between 0 and 1 where this measure is a finite number. That we are going to discuss now. Before that, we will discuss some basics properties of the Hausdorff measure. The scaling property of the Hausdorff measure. The scaling property of length, area and volume are well known. On magnification by a factor lambda, the length of the curve is multiplied by lambda. The area of a plane region is multiplied by lambda power 2, and the volume of a 3-dimensional object is multiplied by lambda power 3. As might be anticipated, S-dimensional Hausdorff measure scales with a factor lambda power s. That means, if lambda is multiplied with the set F, then S-dimensional Hausdorff measure must be multiplied with S. This is the property which we are going to discuss. Such a scaling property are fundamental to the theory of fractal. So, listen here, if we have the curve here, then if you are multiplying lambda, then the curve becomes like this one. It depends on the lambda. One can note that if lambda is greater than 1, then this curve will be enlarged, whereas this lambda is less than 1, in between 0 and 1, this will be reduced size, this will be compressed size will get. But here we are considering lambda is greater than 1, that so that the figures are larger than the given one. If we are multiplying this lambda with this figure, the area of this one, then this figure transform to like this one. And in general, if you are taking the n dimensional object, if you are multiplying with this one, then we will get like this. But that means if this has a measure hs of f, if this is our f, if you finding the hs of f, it has some quantity hs of f. If you multiplying lambda with this f with the lambda, all the lambda is multiplied with f, then what is the measure of hs of f? That means the hs of f will be multiplied by lambda power s of hs of f. This is the property which we are going to prove now. The scaling property of s dimensional Hausdorff measure. If f is a subset of r power n and lambda is greater than 0, the positive real number, then hs of lambda times f equals lambda power s times hs of f. That means where the lambda f is defined as all the member of f is multiplied with the lambda. That means the set f scaled by the factor lambda. One can note that we are taking lambda as greater than 0, the positive real number. Now, if ui is a delta cover of f, then from the each ui, in the each open covering, that means a diameter delta, you can multiply with the lambda, then the lambda u is a lambda delta cover of lambda f. That means if you have the f, for this f you can multiply it with lambda. This f has the sum cover, that is called the delta cover of f. This f has the one cover, that is mu I. That means union of ui is contains the set f. If you are multiplying this with lambda, this is the delta cover, then each delta is multiplied with the lambda, then the lambda times delta cover of lambda f. This will becomes the, maybe you can call it the epsilon cover, where epsilon equal to delta times lambda of the set lambda times f. Hence, the h delta, that means you can call it as epsilon, h epsilon of s of lambda times f less than or equal to this quantity power s. So, here the lambda power s is the constant, you can take it out, we will get this one, then this is nothing but the delta cover of f, therefore one can get lambda power s time this quantity will get. So, if you are multiplying lambda with f, then the measure is multiplied with lambda power s, we are getting less than or equal to. Since this hold for any delta cover ui, let this delta tends to 0 gives that hs of lambda of f less than or equal to lambda power s times hs of f. For the reverse, because we need to find the equality, for the reverse process, replace lambda by 1 by lambda. You can take epsilon cover of lambda f, that means a lambda time delta cover of this quantity. If you are multiplying this one by lambda, then it will be the cover of F. Then same argument one can get the Hs of F, one can get, which is less than or equal to Hs of lambda F. Here Hs of lambda power S, one can get this one. Only thing, instead of lambda we need to get 1 by lambda. Then combining these two things, one can get this, both the quantities are equal. So Hs of lambda time F, one can get lambda time S time Hs of F. One can arrive this equality. That means the second proportion, the proposition for 1, let F is a subset of R power n, and define the mapping F1, the capital F m to R power m be a mapping such that modulus of f of x minus f of y less than or equal to c time x minus y power alpha. Like that we are defining the mapping F. For any constant c and alpha greater than 0, that means any two positive real number, this mapping is defined like this one. Then for each s, then Hs over alpha of f of f less than or equal to s power c power s of alpha times Hs of f. We need to prove this one. If mu is a delta cover of f, if ui is the delta cover of f, then if you can find the image of f intersection ui, which is less than or equal to the modulus of this one, that means the diameter of this image is less than or equal to c time ui power alpha. It follows that this cover is a epsilon cover of f of f, where epsilon is c time delta power alpha. Thus, you can take the sum of the diameter of f intersection ui under the image f power s of s over alpha, which is less than or equal to c power s by alpha time this quantity. So that taking the infimum, and we can get this inequality. If delta tends to 0 and epsilon tends to 0, it gives the inequality 5. What this theorem says, let me explain orally here. Let f is a subset of R power n and f is a function on f, be a mapping such that this property is satisfied. For any positive constant c and alpha, the s dimensional, for each s, the Hausdorff measure is defined as Hs over alpha times f of f less than or equal to c power s over alpha times Hs of f. For proving this one, first take a delta cover of f. So if f is our set this one, then u1, u2, u3, un and ui's and ui plus 1. If you are taking the union of this one, it covers the set f. Therefore, the diameter of all such that this diameter is less than or equal to delta. This is the delta cover of f. Now look at the image of f intersection ui. That means modulus of f of x minus f of y less than or equal to c times modulus of x minus y power alpha. Then if you are finding the image f of f intersection ui is less than or equal to c time ui power alpha, because this f intersection ui contained in this ui. So one can get c time modulus of ui power alpha, which is less than or equal to c time delta power alpha, because each one is the delta cover. Now the images are under the mapping f intersection u1 of f, the image of f intersection u1, f intersection u2, and these are all covers the f of f. Each has the diameter c times delta power alpha. So you can take the epsilon cover for f of f such that epsilon is c times delta power alpha. Then compare the sum of modulus of fn of f intersection u power s over alpha, which is less than or equal to sum of c times ui power alpha times s over alpha. This alpha will cancel again. Then one can get c power s over alpha time this quantity. Now taking the infimum overall all the delta cover, h epsilon of f that we are taking the ui cover, infimum over all the epsilon cover of f, then from here one can get this quantity, which is less than or equal to c power s over alpha times hs of f. So the delta tends to 0 and the epsilon tends to 0. So one can get h power s of alpha times f of f is less than or equal to this quantity. That means if modulus of this quantity, you can observe f shrinks the distance like modulus of x minus y power alpha. So the diameter shrinks like ui power alpha, and the s dimensional constant scaling like modulus of ui power alpha power s over alpha can be written as ui power s up to the scaling c power s of alpha. That means the dimension get divided by this quantity alpha. That is the takeaway. If this is the f is a mapping with this constant alpha, then the dimension is divided by this quantity alpha, factor of this factor c s power s over alpha. Now there is a particular case for this one. Suppose in this condition 4 is known as the Holder condition of exponent alpha. This is called the Holder condition with the exponent Holder exponent alpha. If alpha equal to 1, if in particular case if alpha equal to 1 here, then you will get modulus of f of x minus f of y. That means the distance between the image of f of x and f of y less than or equal to c time distance between x and y. This is called the Lipschitz mapping. In particular, if this c is lies between 0 and 1, then this mapping is called the contraction mapping. Then again the s dimensional Hausdorff measure inequality is true, because we are taking alpha as 1, then it becomes hs of f less than or equal to c power s time hs of f. Any differentiable function with bounded derivative is necessarily Lipschitz as a consequence of the mean value theorem. If f is a isometric, that is modulus of, that means the distance between fx minus fy is equal to distance between x and y, then the measures gets equal. S dimensional Hausdorff measure of f and its image both are equal. If f is isometry on f, then the measure of S dimensional Hausdorff measure of f equal to the S dimensional Hausdorff measure of image of f under the mapping f, both are equals. More precisely, Hausdorff measures are translation invariant. That means if you multiply a number z with the add the z with all the member of x, then the Hausdorff measure doesn't change, and rotation invariant as would certainly be expected. This is the Hausdorff measures are translation invariant. That means you are just translating the set f from one side, just shifting the set 1 here to position like this one here to here, then the h's of f plus z equal to h's of f. Now, in particular you can think about if s is less than 1, so what is the behavior of this mapping, one can think, we will discuss it later. Now, let us define what is the Hausdorff dimensions. Just you can return to equation 1, that means S dimensional Hausdorff measure. It is clear that for any given set f and delta less than 1, h's of f with respect to the delta is a non-decreasing with s. Whenever this delta approaches to 0, h's of f, this delta, this quantity increasing, that we proved in the last lecture. So, by 12, h's of f is also non-increasing. In fact, if t greater than s and ui is a delta cover of f, then the sum of modulus of ui power t less than or equal to this quantity delta power t minus s time sum of modulus of ui power s, because t is greater than s. So, taking infima, so one can get h t of f less than or equal to h's of f multiplied with this quantity delta power t minus s. Taking the infimum of here, one can get this quantity. Let delta tends to 0, we see that this h's of f is less than infinity, then ht of f equal to 0. If h's of f is less than infinity, then ht of f equal to 0 for all t greater than s. Thus, a graph of h's of f against s shows that there is a critical value of s at which h's of f jump from infinity to 0. If you are taking t is greater than s, then h's of f is less than infinity, then ht of f equal to 0. Therefore, in between s and t there is a critical point where the Hausdorff measure is 0. That critical value is called the Hausdorff dimension or Hausdorff-Biskovich dimension of the set f. It written as dh of f. dh of f, we can write it as a dh of f. Now, you can see this is s. Whenever this delta approaches to 0, then dh of, there is a critical point where if you are increasing the delta, if you are increasing the s, this measure goes to 0. This measure goes to 0. When you are decreasing the measure with this critical point, this measure is infinity. Therefore, there is a jump point, that means where this s dimensional Hausdorff measure of f jump from the infinity to 0 is called the Hausdorff dimension. It is denoted as dh of f. This critical point we can write as the Hausdorff dimension of f. Formally, this can be written as infimum of s, h's of f equal to 0. See, there are infinite number of points where this h's of s is 0 here. Among all, we need to take the infimum, and here h's of s is infinity. Among all, we need to take the supremum. That infimum of this set and supremum of this set having the common point, that we can call it as the Hausdorff dimension of the set F, where with respect to this F, the Hausdorff S dimensional Hausdorff measure is finite. That measure we can call it as that point, that critical point S, we can call it as the Hausdorff dimension of the set. So Hs of F is infinity to 0, where it jump from the infinity to 0, that critical point we can call it as the S dimensional Hausdorff measure. If S equal to dH of F, then Hs of F may be 0 or infinity and may satisfying the some positive number. If you are substitute this one, then it has infinity or 0 and it lies between 0 and infinity. Now for a very simple example, let F be a flat disk of unit radius in r power 3. Flat disk of unit radius in r power 3, then H1 of F, that means length of F is infinity. As we discussed in the previous lectures, the geometrical meaning of the Hausdorff dimension we have discussed, in which we have seen that if you are taking the surface, that surface cannot be covered by the finite line of line segment. Likewise, we are taking the unit radius disk in r power 3, like a 3-dimensional object. We cannot cover this one by the finite number of circles or length, therefore the length of F is infinity. And second one, H2 of F, if you are finding the H1 of F, it is length is infinity. If you are taking H2 of F, it is 5 by 4 times area of F, area of the unit disk. If H3 of F is the 1-dimensional measure, it is infinity. Then 2-dimensional measure, it is a finite number, lies between 0 and infinity. If you are taking H3 of F, 4 by 3 times 5 into volume of F, which is equal to 0, because we are taking the unit disk. The unit disk is like this one, unit disk. That means set of all x comma y such that distance between x and y is we are taking the unit disk with radius, it is less than or equal to 1. Suppose we have the point x is x1 y1 and y is x2 y2, then the distance in r power this one can be written as x minus y is the square root of x1 minus x2 power 2 plus y1 minus y2 power 2. The distance is like we are defining like this one. This is the we are taking as the unit radius, therefore the radius is 1, the center may be any point. The distance between any 2 points, the pair of points, that means this is the pair of point, the distance between x is the member of r power 3 and y is the member of r power 3, then we can get this one. This unit disk, that means x square plus y square is less than or equal to 1. If you are taking the center as 0, that means x comma y at center 0 comma 0, one can get this unit disk. This unit disk area is finite area in 0 comma infinity, therefore the 2-dimensional measure is a suitable measure for this one. The finding the area is suitable, whereas if you are finding the length, it cannot be covered by the finite number of circles. We cannot cover this disk by the finite number of circle, we need the infinite number of circle, therefore the length is infinity. If you are finding the volume, one direction is 0. In r power 3 we are considering this disk, therefore other direction is 0, therefore volume becomes 0. Thus the Hausdorff dimension of f equal to 2 with hs of f equal to infinity if s less than 2. If s is less than 2, the Hausdorff measure is infinity. If s is greater than 2, the Hausdorff measure is 0. So, for the any two dimensional object, in our yesterday we consider the line in the space as well as the surface in the space. So, space means it is r power 3. Now, we are consider in r power 3 consider the unit disk. Unit disk, that means the radius 1, the center at 0, 0, maybe anything which we are drawing here at the center 0, 0. Now, here if you are finding the length, it is infinity and the area is finite number, the volume is 0. Therefore, for this type of smooth object, studying area is the useful measure. Let us discuss some properties of Hausdorff dimension. Then we will find there are some sets. Here you can note that the Hausdorff dimension of the unit disk is the integer number 2. Now, we need to know, so what is the Hausdorff dimension of some strange sets like by the fractal type of states, what is the Hausdorff, whether it is always an integer or non-integer number, that we need to discuss. For that, let us discuss some properties of the Hausdorff dimension. If f belongs to r power n is an open, then the Hausdorff dimension of this open set is always n. Since f contains a ball of positive n dimensional volume, then smooth set, if S is smooth, f is a smooth, that means the continuously differentiable, m dimensional submanifold, that means m dimensional surface of r power n, then the Hausdorff dimension of f equal to m. Say for example, our previous example we consider in r power 3 considering the unit disk, it has the Hausdorff dimension 2 where it is embedded in r power 3. In particular, smooth curve has line dimension 1 and smooth surface has the dimension 2. That if you are taking any curve in r power 3, it has the dimension 1. And if you are taking any surface, then it has the dimension 2. So, in general, if f is a smooth, that means continuously differentiable m dimensional submanifold of r power n, then that Hausdorff dimension of f equals m. Now, the monotonicity property. So, already we discussed the monotonicity property of the s dimensional Hausdorff measure. Now, we discussing the monotonicity of Hausdorff dimension. If E contained in F, then the Hausdorff dimension of E less than or equal to Hausdorff dimension of F. Maybe you can compare these properties with already we defined what is the fractal dimension in terms of box counting method. We defined what is fractal dimension. Keep in mind the fractal dimension also satisfying all these properties. This immediate from the measure property that Hs of E is less than or equal to Hs of F for each S. Therefore, this if your E contained in F, then we can say that the dimension of E is less than or equal to dimension of F. Then countable set. If F is a countable, then it Hausdorff dimension is 0. For if f is a single point, that means any finite set, then h0 of f equal to 1. That means it counts the number of points, and which we already discussed, the 0 dimension of the finite set is, it gives the number of points. Here we are taking f as a single point. Therefore, h0 of this not an fi, the f is 1. If this is 1, the h0 of f is 1, then the dimension is 0. That means f any single point, that means any finite set has the dimension 0. Also if the set is countable set, then its Hausdorff dimension is 0. So by countable stability we can prove that the union of I equal to 1 to infinity fi for this dimension equal to 0, because each single set is dimension 0. It is f is a single set, this is true. Therefore here if f is a countable, that means it has some countable union, that means union of set, then each fi is 0. Therefore it can be covered by this set. If this is 0, then the measure of df Hausdorff dimension of f is 0. Then countable stability, this is the countable set, the Hausdorff dimension is 0. Now countable stability, let fi be a sequence of sets in R power n, then the Hausdorff dimension of union of all the sets equal to supremum of I the dimension of fi. For the lower bound, suppose fi is contained in union of fi of f, then as per the previous property we can say that Hausdorff dimension of this set is less than or equal to Hausdorff dimension of this set. Then which implies supremum of I d h of fi is less than or equal to the Hausdorff dimension of union of I fi. Now this quantity is less than or equal to this quantity. For the upper bound and other side, let S be any number greater than the supremum of dh of fi, then hs of fi equal to 0 for all I, because this is the Hausdorff dimension. If we are taking greater than S is greater than this quantity, then hs of fi equal to 0 for all fi. Hence hs of union of this one is less than or equal to sum of hs of fi, which is equal to 0, therefore which is less than or equal to S. The dh of union of fi less than or equal to S. So which implies that dh of union of fi equal to supremum of dh of fi. That means we are taking the supremum among all the things, then you will get the union, which we already discussed in the box counting method. If we are taking A union B and the dimension of A, box counting dimension while defining, that means the fractal dimension, if A union B, if A has the higher dimension, that means a dimension of B is less than or equal to dimension of A, then dimension of A union B equals dimension of A. That means then higher dimension set dominates the union. Likewise here you can see the countable stability of the Hausdorff dimension. Now if f is a Lipschitz transformation, then the image of f, the dimension of image of f is less than or equal to the dimension of f, that means Hausdorff dimension of f. The Hausdorff dimension of image of f is less than or equal to dimension of f. The Lipschitz means that modulus of f of x minus f of y is less than or equal to some c times x minus y, where c is the any positive number. You can think when we will get the equality. If it is isometry or is c is less than 1, we can get something nice result from here. If f is a bi-Lipschitz transformation on f to r power m, so there exists a constant c1, c2 such that the distance between xy is less than or equal to distance between fx, fy and less than or equal to c times distance between x and y, where c1 is less than or equal to c2, both are the positive real constant. Then the dimension of f of f and f both are equal. That means the Hausdorff dimension is preserved by the bi-Lipschitz transformation. This both the property we can prove in the proposition 1. You can take alpha as 1, one can get the S dimensional Hausdorff measure property, one can prove this one applying to F inverse and this here, this one can get this one. So from here one can understand that the bi-Lipschitz transformation preserves the Hausdorff dimension. That means this corollary reveals a fundamental property of Hausdorff dimension. Hausdorff dimension is invariant under bi-Lipschitz transformation. Thus, if two sets have different dimension, there cannot be a bi-Lipschitz mapping from one onto the other. This is the reminiscent of the situation in topology where various invariants such as homotopy or homology groups are set up distinguished between sets that are not homeomorphic. If topological invariant of such set differ, then there cannot be a homeomorphism. That means continuous one-to-one mapping with continuous inverse between the two sets. So it reflects the same in the Hausdorff dimension with respect to the bi-Lipschitz transformations. Now let us discuss some property of the set F with respect to their Hausdorff dimension. Now we are going to discuss what is the topological property of the set F with respect to their Hausdorff dimension. Now you can take a set F belongs to R power n with the Hausdorff dimension is less than 1 is then the set F is totally disconnected. You can take a set F in R power n. If this set has the Hausdorff dimension less than 1, then set is totally disconnected. For this, let x and y be distinct point of F. We are taking two distinct point of x, that means x and y not equal, which are both belongs to F. Define a mapping F from R power n to open interval 0 comma infinity by, if you are taking z, then find the distance between z and x. Since F does not increasing the distance, F does not increasing the distance. For proving this one, you can take two element, then take the two element z and w, find their image, then modulus of f of z and two element in R power n, then find the distance f of z and f of w. We are considering R power n with the Euclidean metric. This norm denote the Euclidean distance. Then this can be written as f of z minus f of, if you are taking the two elements, then this two element is, the mapping is defined as z is minus with x and w is minus with x. That means this becomes z modulus of z minus x minus modulus of w minus x. This is like modulus of a minus modulus of b. So which is less than or equal to modulus of a minus b, z minus x minus w plus x. So which is less than or equal modulus of z minus w. So if you are finding the distance between the image of z and y, then it is not, it is greater than the z minus w. If you are taking the distance between these two number, it is always lesser than the original distance between the original number. So since f does not increase the distance, therefore that means f of modulus of f of z minus f of w, one can write modulus of z minus w. We have the corollary 2a. This is like a Lipschitz mapping with C equal to 1 and in the Holder exponent alpha equal to 1. Then the Hausdorff dimension of image of F is less than or equal to Hausdorff dimension of F, which is less than 1, which is less than 1, the constant. Thus, f of F is a subset of R of H1 measure, that means 0 length 0, and so has a dense complement. Choosing R with R does not belongs to f of F and R is less than f of y, it follows that F can be written as set of all Z belongs to F such that the distance between Z and X less than R union Z belongs to F, that Z minus X greater than R, union of these two set. We can write F as the union of these two state. The F is containing in two disjoint open set with X is one set and Y is in other set, so that X and Y is lies in different connected component of F. We are taking with X and Y are two distinct point and both are lies in the two different connected component. That means if you are taking any two element, if we able to find two connected component, one is lying in the other component and another is another component, then we can say the set is totally disconnected. So that here if the set F has the box counting dimension is less than 1 as per here, then the set is totally disconnected set. So thank you. I will stop here. We will discuss in the next lecture. These are all some references. Thanks.